In this video, I will explain the basics of what is a laser, its properties, and the principles on which a laser works. For example, what is stimulated absorption, spontaneous emission, stimulated emission, and the most important one is the population inversion, which is a basic condition for lasering action, and how we achieve the population inversion. As you all know that the word laser stands for the light amplification by stimulated emission of radiation. That is what I mean by the word laser. But how we basically amplify the light, how we amplify the light using stimulated emission. Okay, so we will discuss all these here. You can consider it like very crudely if I say that if we have a light bulb, if I have a bulb which is emitting radiation of red color and which is moving in all directions, then and naturally all these are obviously monochromatic, because all these light which is coming from this bulb are having the same wavelength. So this light is going in all directions, but if somehow we manage to direct all this light into one direction, okay, in one direction, okay, then what we will get? So if we manage to direct all these light into one direction, then we'll get an intense beam of light. Okay, and this is what we do in a lasering process. So that this is what we do in laser. So a laser is a device that produces light beam with some remarkable properties, and the first one is laser is a very nearly monochromatic. Okay, what do we mean by the monochromatic? That you can see here in monochromatic, incoherent, monochromatic. If you consider the monochromatic means if we have a beam of light ray, then each and every ray of light in the beam is having the same wavelength. Because if you consider on this, its wavelength is like from here to here, this is its wavelength, and here to here this is wavelength, here to here this wavelength, all these are same. The wavelength is same for each and every ray in the light beam, not like the ordinary. If you consider in the ordinary light beam, so its wavelength is from here is this wavelength, and this is, you can see naturally, this is the another wavelength, this is wavelength of this. So every wavelength is different in ordinary light. So this is not a monochromatic. The monochromatic means the every ray which is constituting the beam is having the same wavelength. Okay, so therefore the light uh, in a laser is very nearly monochromatic. The second one is the light is coherent with the waves all exactly in phase with one another. What is the meaning of coherent? And all the waves all exactly in phase with one another. So monochromatic, you know, is already that wavelength has to be same. You can concentrate on this part, that the wavelength is same, wavelength of this is same, wavelength of this is same, wavelength of this, all these wavelengths, say lambda 1, lambda 2, lambda 3, are all same. So coherent means they are all exactly in phase with one another. If you consider of this wavelength, wave 1, wave 2, and wave 3, if you consider wave 1 and 2, the phase is same. The position of the particle which is vibrating at this position is same. If you can any point you consider, the position is same. Phase, they are all in phase. Like here, they are all in same, this point, this point, this point, this point, this point, this point, they are all in same. At every point in a space you will find all these rays are going to have a same phase. So that is what we mean by coherent. So this part of the light wave, in which we have three rays, is a monochromatic because the wavelengths are same. Lambda 1, lambda 2 and lambda 3 are all same, and so on. And the coherent because they are all in phase with one another. This is what we mean by coherency. So coherency can be spatial as well as temporal. So this what I'm talking about in a space. If you consider in a space any point, the all the waves will you will find are all in this phase, and the same goes for if you look the wave with respect to the time. They are all moving exactly in the same manner, in the same phase with respect to the time in space. So it's a monochromatic. Laser light is monochromatic, and the light is also coherent. The third one is the laser beam diverges hardly at all. For example, uh, what do I mean by diverges hardly at all? If for example, if you send such a laser beam from earth to uh, uh, to the moon where you have a mirror, so and the beam, if you send the beam to the moon, and it will strike the mirror which is on the moon and will be reflected back on earth, still it remains narrow enough to be detected on its return to the earth. So you can imagine that such a distance of over 3/4 of a million kilometer, after traveling the beam, and it is still narrow, there is no divergence. You cannot imagine this with a light beam produces by any other means would have spread out too much during the travel. If you throw a torch light towards the moon, it's not going to return to the earth. Like it diverges like after 1 meter or 2 meter. But this is not the case with a laser light. It is it is so intense that it hardly diverges at all. So now you know what is a divergence when I talk about the beam diverges hardly at all. The fourth property is the beam is extremely intense. So the laser beam is extremely intense. If we compare it with the light from any other source like torch, then it will be more intense. What do you mean by intense? Intense, when I say intense, that you're talking about the energy density. And what is energy density? Energy density is the energy stored in the beam per unit volume. So for the laser, if you find the energy stored in a laser beam per unit volume is very high. And if you try to compare it with that part of the laser beam whose energy stored is very high, if you compare with any ordinary light, if you want to achieve that energy stored uh, to such a high energy density, then you need to have that object at a temperature of around 10 to the power 30 Kelvin. So so if you take a laser beam and you see that per unit volume what is the energy density of a laser beam, and if you will take some other ordinary light, and if you want to have the same energy density per unit volume, then that portion of the light has to be at the temperature of 10 to the power 30 Kelvin nearly, and this is almost impossible. So that's why the beam is extremely intense of the light. And you see the two properties, its divergence and its intense, being intense, follow from the its property of all the rays of the laser beam being coherent. So these two property, divergence and intensity, directly comes from its coherency, the property of coherency. If it's not coherent, it's not going to be diverged, it's not going to be intense, because when it is coherent, it is monochromatic and in phase. So everything is in phase, going in space and all in space and time. So that way it hardly diverges, and that's why its energy density is very high. So uh, this is what about the light amplification by stimulated emission of radiation and its properties. So now let us move to understanding the basic procedure or process which are involved in the lasing action to occur. First of all, let me tell you that an atom can exist in any of the three energy levels. You can see as shown in this picture, all these. So what I'm telling that if you have an atom, then it can exist in any of the three energy levels, which I'm going to talk about. The first one is the ground state. This is the ground state. This I'm talking about the ground state. Okay, this is my ground state. And what is ground state? We all know that that at thermal equilibrium, I suppose that you know what is thermal equilibrium. Something is at equilibrium with respect to the temperature. So all the atoms at thermal equilibrium, all the atoms are usually exist in the ground state and remains there. So if you have some system, then all the atoms of the system are supposed to be in the ground state. All the atoms are supposed to be in the ground state when something is at thermal equilibrium, all the atoms of the system. Okay, so that is what we consider as a ground state. So at thermal equilibrium, all the atoms are supposed to be in the ground state. This is what we knew what is ground state is. That's the lowest energy level which can exist in a system. The second one is uh, the ordinary excited state. So we will consider that it at the ordinary excited state. Okay, this ordinary excited state. So this state basically it's an excited state, and what I mean by excited state is the energy level which is having energy more than the ground state, and it's the upper level, and ground state the lower level, and this is the upper level. But the important factor property which is associated with the excited state is about its lifetime. Thus, the lifetime of an ordinary excited state is of the order of 10 to the power minus 8 seconds. 10 to the power minus 8 seconds. What do you mean by the lifetime? Lifetime means if some atom is there, this suppose this atom is there in this ordinary excited state, then after spending 10 to the power minus 8 seconds, this atom will drop down to this level. Okay, okay, we'll talk about all these later on. So this is what we mean by lifetime. If you stay there in this, you can only stay for 10 to the minus 8 second. After that, you will automatically come back to this some other level which has to be lower to this ordinary excited state. This is what we mean by ordinary excited state. Now the next is metastable state. That is also this is also an excited state of an atom. This is a state. Okay, this is a state within the ordinary excited state which had its lifetime greater than the ordinary state. Okay, so lifetime of this metastable state, like here this the metastable state is greater than the ordinary excited state, and it is of the order of 10 to the power minus 3 second. So 10 to the power minus 5 second is greater than 10 to the power 5 second greater than the life of the ordinary excited state. So this state has a major role to play in the lasing process. Okay, so excuse me. So ordinary state has a 10 to the power minus 8 second of lifetime, and the metastable state, which is also among the excited state, but it's just going to have a lifetime of 10 to the power minus 3 second. And this state has a major role to play in the lasing process. These metastable state, mind it, these metastable state usually are present in the mixture of gases or compounds. Okay, if you consider some atom, in an atom you are not going to find the metastable state. But if you have a combination of atoms of different elements or gas or compounds, then only you are going to get a metastable state within the excited state of this compound or the gas. And this is these gases or compounds which are going to play the role of the active medium for lasing action. So within this medium only you can find the metastable state, and if you have a metastable state, then only you can find the laser action. So the medium in which we choose our metastable states to achieve the lasing action is known as the active medium. The word I am using is active medium. So that means, what is an active medium? Active medium is in which if we choose our metastable state to achieve the lasing action. That is what we meant by the active medium. So now we know that if I have a system or an active medium, we are going to have a three kind of energy level or a state. That is, one is the ground state, in which we generally all the atoms are supposed to be there because it's the lowest energy level, and then the ordinary excited state, which is tagged with the lifetime of 10 to the minus 8 second. Then we're going to have a metastable state whose lifetime is 10 to the power minus 3 seconds. Fine. Now let us discuss the three different types of transitions involving the electromagnetic radiation which are possible between the two energy levels. First, consider this. This is my energy levels with energy E naught, and this is the energy level with energy E1. So if we consider we have a two energy levels with energy E naught and the energy E1, then what type of transition are possible with electromagnetic radiation between these two energy level E0 E1 of an atom, as shown in the picture, in this picture. The first one we are going to discuss is the stimulated absorption. The stimulated absorption, this transition. What do you mean by stimulated absorption? Uh, we know that at thermal equilibrium, all the atoms are used to be in the ground state. Okay, which is in this case is having energy E0 as shown in this picture. So all the atoms, as I said you, at thermal equilibrium, all the atoms are supposed to be in the ground state. If you suppose this is my E naught is the ground state, then all the atoms are here present in the ground state. Okay, now one of the atom which is initially in the ground state, which is the lower state, say ground state E0, if you provide an energy, and if you provide this energy, say this is energy provided by a certain photon or electromagnetic radiation of of energy h nu, that is E equal to h nu. This is the energy which I am providing to one of the atom which are in the ground state. If you provide this energy, then the atom absorb this energy, one of the atom absorb this energy and become excited and move to the upper state here. If suppose this atom provide this atom absorbs the energy and then it moves to this excited state. Okay, so this atom moves here by absorbing the energy which I have provided it. The provided energy must be equal to the difference of energy between the lower state and the upper state, which is delta E. Say delta E, we normally write it as E1 minus E0, which is H nu 10. So going from 1 to 0. So this is the delta E, which is the energy difference between these two energy levels, E1 and E0. Okay, so if we provide this amount of energy H nu 10, which is the difference between the energy level E1 and E2, then some atom of which is in the ground state absorb this energy and move to the next excited state. Say in this case this is E1. Such process is known as the stimulated absorption, that I am stimulating the atom which is in the ground state by providing an energy, and this atom absorbs this energy and moves to the excited state. Otherwise, when I am not going to stimulate it, these atoms are going to be remain in the ground state. So the kind of I am stimulating this atom to absorb this energy which is I am providing, and it moves to the next excited state. This process is known as the stimulated absorption. The second one is process is the spontaneous emission. Spontaneous emission. Okay, so the word spontaneous is there. Okay, so that means something is happening spontaneously. I'm not going to stimulate anything. So this atom, so this atom which is already there in the excited state, and I know this is, suppose this is an ordinary excited state. Suppose right now this excited state is some ordinary excited state, ordinary excited state of lifetime 10 to the power minus 8 seconds. So what will happen that if this atom is already in this excited state, then after 10 to the power minus 8 second, okay, this will automatically come back to the ground state. You don't have to do anything. So after spending a time of 10 to the power minus 8 second, it will automatically come back to the ground state. So after this lifetime, it will spontaneously drop down to the ground state E naught. In the process of coming down to the ground state, it emits a photon of the same energy. It is emitting a photon of the same energy, this one, because the energy, it will emit the photon of the energy which is equal to energy difference between this state and this state. But this photon is incoherent in comparison to the one which the atom has moved to the upper state. This is called the spontaneous emission. What I'm saying that this, the process, if you see the picture of this process, if I shine a photon of energy h nu, and then this atom absorb this energy and absorb this energy and move to here in the excited state, and after spending 10 to the power minus 8 second, it automatically comes down to the ground state. Okay, to the ground state. But the photon through which I have stimulated this atom to go to this state, and the photon which is coming when this atom is spontaneously coming to the ground state, these two photon, this photon and this photon, are incoherent. They are incoherent. These two photons are incoherent. Incoherent means they are not in phase with each other. There is no relation between this photon and this photon. They are not in phase with each other. So this is another process which is a spontaneous emission, in which the atom which was already in the excited state, and after spending a time 10 to the minus 8 second, it spontaneously decay to the ground state, and while in decaying process, it emits a photon of the energy which is equal to the energy difference between the upper energy and the lower energy. This process is known as the spontaneous emission. The third one is very important, which is basically responsible for the lasing action, is stimulated emission. Okay, as the name suggests, the stimulated, that means I am stimulating it for what? For the emission of the photon. So the third possibility of transition is a stimulated emission, and this possibility is uh, put forward by the Einstein in the year 1970. Okay, this was put forward by Einstein in 1917. Okay, so in what happens in this process? In this process, an incident photon of energy h nu. So suppose we have an atom in the excited state. Now here in this case, this is my could be my ordinary state or could be my metastable state. Okay, either ordinary or metastable state. Okay, fine. But this is the atom which is initially in the excited state. Okay, fine. If we shine uh, a photon of energy, some h nu, which is this one, which is naturally equal to the energy difference. Energy is equal to the energy difference between this level and this level. If we shine this photon, then what this photon does, it stimulate this basically it strike this atom and stimulate this atom, uh, or sort of push this atom from the upper state to the lower state, and this atom comes down to the ground state. So what happened in this process, we have two photon in the final state. One photon which is coming, which is used to push this atom from the upper state to the lower state, and the one photon is there when this atom is coming down to the ground state. While coming down, it emits a photon of the same energy. Okay, so say this one is, so this one is which is used to stimulate this atom, and this one is used to, this one is coming while this atom is coming from upper state to the lower state. So the important thing is that these two photons of the same energy are in phase. These are coherent, in phase with each other. So by supplying one photon, I am getting a two photon in the final state. Okay, so what happened that in the stimulated emission, the radiated light wave or photon is exactly in phase with the incident photon, which has stimulated the atom in the upper state. So as a result, for one incident photon in the final, we get two photons which are in phase with each other. Further, when these two photons stimulate two other atoms in the upper state, we get four photons. So suppose you can see that we have in this picture we have a large number of atoms. Such large number of atoms are there. So one photon comes and stimulate this atom, and we get a two photon. And what happened, this photon, suppose like this photon stimulate this atom, and then again from here we'll get another two photon, and this will go here and stimulate, we get another two photon, and similarly there will be a large number of photon. Okay, so further, when these photons stimulate two other atoms in the upper state, we get four photons in the final state which are in the phase. So all these photons are in phase, so we get an enhanced beam of coherent light. This is exactly how we get a laser beam inside the cavity of a laser. You can see this process happening in this GIF file, where the large number of atoms are present in the excited state, and the process of stimulated emission giving rise to more and more number of photons which are in phase. So that is why stimulated emission is important, because giving with one photon I'm getting two photon, and when these two photons I'm getting four photon, and with this four photon I'm getting eight photons. So there is a multiplication enhancement of the number of photons, and the important thing is that all these photons are in phase with each other, so that is they are coherent. So if I somehow manage to capture these photons and try to build a large intensity, high intensity beam, and so this will naturally going to give me a laser beam which is coherent, which is monochromatic, and which is intense. And so this process is important, and this process is only responsible for the lasing action. One thing you must note that the Einstein showed that the stimulated emission has the same probability as the stimulated absorption, because what I must say that this process is stimulated emission, the probability of stimulated emission is same as the probability of stimulated absorption. This has been shown by the Einstein. This means that, what I mean by saying the same probability, this means that a photon of energy h nu. So if you suppose if a photon of energy something h nu is incident on uh, uh, the atom, say incident on the atom in the upper state, which is in the upper state, say this is my E1, has the same likelihood of causing the emission of another photon of energy h nu uh, as its likelihood of being absorbed if it incident on an atom of lower state, say E naught. So this is, say this is E naught, this is E1. So let's try to understand this. What I mean by saying the stimulated emission and the stimulated absorption has the same probability. So when I have one photon, so if I am saying that this photon is going to stimulate this atom which is already in a state E1, and when this photon is stimulating this atom, and this will come down here, okay, this will come down here and it will emit a photon. So there's a probability that this photon is, we can think of the same probability that this photon is also going to stimulate this atom to absorb this and go to the upper state E1. So because you are not going to see inside the system, that you are just shining a photon, that there is an equal probability that this photon can stimulate this atom which is already in the excited state, or it can also stimulate this atom which is already in the ground state. So when this atom is stimulating this which is in the ground state, and it will go to upper state, then this is your stimulated absorption, and it is exactly going to have the same probability that this photon is can stimulate the atom which is already in excited state, and this atom will come to the ground state, which is the stimulated emission. So that is why the Einstein showed that the stimulated emission has the same probability as the stimulated absorption. Okay. Actually, the stimulated emission involves no novel concept. So you can understand it with an analogy, very simple analogy, which is an harmonic oscillator. For instance, you can consider a pendulum. So a pendulum has a sinusoidal force applied to it. So if you have a pendulum, let us suppose where to make it. If I have a pendulum, say let's make it, if I have a pendulum, simple pendulum, which is swinging down, so it will go to this side, it will go to this side, okay. So this is a kind of simple harmonic motion, okay. So going up, coming down, going up, coming down, this is like, this is mean, right? This is going up, coming down and going up, okay. This is sort of process is going on. So if I applied a force whose time period the same as the natural period of vibration, okay, so what will happen? So if I applied a force and the nature of the force is same, say let's say if I applied a force which is let me, so if I applied a force which is exactly having the same phase, what will happen? This will add up to a large amplitude, okay. So if the period of the force is exactly in phase with the pendulum swings, the amplitude of the swing increases. So this corresponds to the stimulated absorption, okay. That means it absorbs and goes to there. The second is, however, if I applied a force which is not in phase with it, it's like it is like, say it is uh, say out of phase with 180°, then what will happen? We're going to get a straight line. the amplitude will decrease, and this corresponds to the stimulated emission. This is very simple analogy. So now you know that what is the three different processes which are involved with the electromagnetic transition going to do between the two energy levels. Okay. The next important thing is, which is very important, is about the population inversion. Population inversion. Okay. So normally the word population inversion is describe a system of atoms when is in thermal equilibrium. There are always more atoms in the low energy state or the ground state than in the higher excited state. So if I suppose that this system is in thermal equilibrium at this time, and we have more number of atoms, like 1 2 3 4 5. This is my ground state, say this is E1. E1 is my ground state, say this is the ground state. So when the system is in thermal equilibrium, there will be a more atoms in the ground state with respect to the any excited state, E2 or E3. Okay, so if I say N1 is the number of atoms in the ground state, N2 is some in the excited state, N3 in another excited state. So N1 will be so number of atoms N1 will be greater than N2 or N3 always at thermal equilibrium. Fine. So the term population inversion describe the redistribution of atoms in the atomic energy levels such that there are greater number of atoms are in energy levels above the ground state, that is in excited state. So this excited state is in general chosen to be one of the metastable state. So what is the population inversion? Population inversion is the process describe the redistribution of atoms in the energy level. And how we redistribute the energies? That means we shine a photon, and then atoms are going to absorb this photon energy and will go to some excited state. Okay, will go to some excited state. Fine. And then, so say that this is E3 is some ordinary excited state and E2 is metastable state. Okay, ordinary excited state and E2 is metastable state. So the population inversion is maintaining more number of atoms in as compared to the ground state. This condition is known as the population inversion. So when I say that ordinary excited state is having a life of time of 10 to the power minus 8 second, and this metastable state is have lifetime 10 to the power 3 second. So if I do the stimulated absorption, in which the atoms which are in the ground state absorb the energy given by the photon and they move to the ordinary excited state, and then after spending 10 to the minus 3 second, these atoms spontaneously comes down to the metastable state. And this process from some ordinary excited state coming down to the metastable state, this in this process is normally known as the non-radiative process. This is non-radiative transition, in which we are not going to get any radiation. Spontaneously, these atoms which are in the ground upper excited state are coming down to the metastable state. And so since the lifetime of the metastable state is 10 to the minus 3 seconds, so naturally the atoms are going to spend more time in the metastable state when coming to the ground state. So naturally we are going to have the more number of atoms in the metal stable state as compared to the ground state, and achieving this condition in which the more number of atoms in the metal stable state as compared to the greater state, actually more than half of the number of atoms has to be in the metastable state as compared to the ground state, and this condition is known as the population inversion. Okay, I think you now understood that what is population inversions. So there are a number of ways which exist to produce the population inversion. One of them is called the optical pumping. So what we do in optical pumping, here an external light source. If I have a light source is used to some of those photons have the frequency, right frequency, to raise the ground state atoms to the excited state, ground state atom to the excited state, and then um, these atoms decay spontaneously from excited state to the metastable state through non-radiative transitions to the desired metastable state. So we basically populate the metastable state by the pathway involving optical pumping and non-radiative relaxation. We can achieve population inversions. So what we do is we do optical pumping in which what we do, we supply energy to the atoms which are in the ground state, and then these atoms, by absorbing the energy, when goes to the excited state, and from excited state spontaneously they decay to the metastable state through non-radiative transition. Okay, non-radiative transition. So then we achieve the population inversion. So this understanding population in is important. Okay, fine. In the next slide we'll discuss that why do we need the population inversion, and many other things, that what are 3-level laser and what are 4-level laser, and why we need 3-level laser. So this is for these three transition: spontaneous stimulated absorption, spontaneous emission, stimulated emission, understanding the ground state, metastable state, and ordinary state, and what is the population inversion, and the optical pumping is the process by which we achieve the population inversion. Let us discuss a 3-level lasing system. So, and then we'll discuss why we need 3-level to have a lasing action, and why we cannot do it with the 2-level. So to understand the 3-level lasing system, which goes like this, that we have the ground state. This is my ground state with energy E0, and this is my excited state. This is ordinary excited state with energy E2, and the lifetime is 10 to the power minus 8 seconds. And then we have a third state which is E1, which is a metastable state of the lifetime 10 to the power minus 3 seconds. So we know already about these three states which exist in an active medium of the laser. So what happens at thermal equilibrium? Most of the atoms are in the ground state. You see, most of the atoms are in the ground state, and when we pump energy, we supply energy in terms of the photon uh, with energy h nu prime, which is actually equal to the energy difference between the 2-level, the excited state E2 and the ground state E0. So when we supply the energy or pump the energy to these atoms which are in the ground state, equal to the energy between these two states, so these atoms absorb these energies supplied by these photons. They move to the excited state here. Okay, This is the first process. By absorbing energy, and the atoms in the ground state moves to the excited state. This is known as the stimulated absorption. Okay, so now after stimulated absorption, what happens when these atoms are in the ordinary excited state E2, and after spending a time of 10 to the minus 8 second, they basically do a spontaneous emission, and this is the rapid transition to the metastable state E1. Okay, by doing a spontaneous emission, and while they come from E2 to E1, they emits a photon. They may emit a photon of energy h nu prime, which is equal to the difference of energy E2 minus E1, or these could be some non-radiative transition, in which we are not going to get any type of radiation. So this is what you have as spontaneous emission. So now you have a stimulated absorption, then you have a stimulated emission, and then the atoms which were in the ground state earlier, through stimulated absorption goes to the excited state, and with stimulated spontaneous emission they come back to the metastable state. So since the lifetime of metastable state is 10 to the minus 3 second, much more than the lifetime of this excited state E2 and the ground state E0, so naturally the atoms are going to be live longer life in the metastable state E1. So if we supply more and more energy to the system in the ground atoms in the ground state, more atoms are going back, going to the excited state here, and then more atoms are coming to the metastable state. So naturally we are going to achieve the more number of atoms in state N1 as compared to the ground state. So here condition is if N1 is greater than N0. So when at least more than half of the number of atoms which are in N0 is there in N1, we achieve the population inversion. And we will achieve the population inversion. What we do, we stimulate the emission. So we stimulate with some photon to these atoms to come down, and for one stimulation we see that there will be two photon, and for another there will be two photon, and then similarly when these two photon will stimulate another two photon, this photon will stimulate another, and this will another, and so on. We have a large number of photon in the final state. So stimulated emission occurs when photons of energy h nu, which is difference of E1 and E0, are incident with the secondary photon themselves, inducing further transition to produce an avalanche of coherent photon. And you know that all these photons which are coming through the stimulated emission, they are all coherent. Coherent means they are all in phase. Okay, so when these photons which are getting enhanced due to some stimulated emission, when you trap these all photons inside the cavity of the laser, this side is a mirror which is fully reflecting mirror, and this side you have a partially reflecting mirror. You see all these photons are getting trapped inside this cavity, and then they are traveling back and forth in this cavity, and they are gathering the energy density, and the moment they get the power with so much of very high energy density, they come back from the partially silver mirror in terms of a laser beam. So this is how we achieve the laser beam when we have a three-level system in which we have a ground state, we have excited state, and we have a metastable state. Now this is, that is why how we with the three-level system we can achieve our lasing action. And let's come to the question that why do we need the population inversion? This is important. Why do we need the population inversion? So as you know that uh, why do we need population inversion? Why do we need population inversion? Why do we need it? So you know that population inversion is required uh, in a laser in order to have the lasing action, because if you're not going to have population inversion, you're not going to have the lasing action. So for the lasing action, what we want is more atoms in the metastable state, more atoms in the metastable state than in the ground state. That is N1 uh, N1, which is the number of atoms in the metastable state, has to be greater than N2, which is the number of atoms in the ground state. This is as a population inversion, and this is required for the lasing action. So if we can arrange this condition and then shine light of frequency h nu on this assembly, as you have already seen here, if you shine the light of the frequency on this assembly, there will be more stimulated emission. Okay, so that we get more and more number of photons uh, through the stimulated emission in the metastable state, and more probable than the induced absorption. So what I'm trying to say is, when more number of atoms in the metastable state is than the ground state. So try to understand this, because the Einstein said that, and I have already explained you that uh, there is a equal probability of stimulated emission and stimulated absorption. That if you shine a photon, there is the probability is same that this photon is either going to get absorbed by the atoms in the ground state. If I shine a photon, there is a equal probability that this photon is getting absorbed by this atom in the ground state, or there is equal probability that this photon is going to stimulate the atom which are in the metastable state. Okay, so there is equal probability. So if the number of atoms are same, if n1 equal to n naught, then there will be no enhancement of the photon, because the number of photon which are which are being used in the stimulated emission is number of photon is equal to number of photon being getting absorbed by the atoms in the ground state. And so we are not going to get a more number of photons in the final state. This is possible only when we have a more number of atoms in the metastable state, so that there is more probability that the photon is going to hit the more number of atoms in the metastable state, and we are getting a more and more number of photon in the final state by through the stimulated emission than the number of photons getting destroyed by being absorbed by the atoms in the ground state. So that is why the population inversion is important. So that the stimulated emission is more probable than the induced absorption when we achieve the population inversion. That is when the number of atoms are there more in the metastable state as compared to the ground state. Thus the photon are more likely to gain more coherent photons in stimulated emission than they are getting destroyed in the stimulated absorption. So the result will be an amplification of the original light, permitting the lasing action. This is the concept that underlies the operation of the laser. Now you know why the population inversion is important. Fine. Now in the next slide, we are going to discuss so why three level is needed. So I think you already know why we need a three level. Suppose there are only two level. Okay, suppose there are only two levels, say E1 and E2. So what will happen? So this is a metastable state in the ground state. Okay, the more photon of frequency h nu, so this is frequency h nu, we pump into the assembly of atoms, the more upward transition there will be from the ground state. Okay, more upward transition from the ground state to the metastable state. However, at the same time, the pumping will stimulate onward transition from the metastable state to the ground state. So the same photon, because the probability is same photon are going to do the going to stimulate all these atoms which are there in the which are being there present in the metastable state. So when half of the atoms are in each state, okay, so if n1 equal to n2, or say when you are supplying the energy, the atoms are going in the E2 state, and then when these atoms are here in the E2 state, they so these photons are more likely to do the stimulated absorption, so that these photons come down. So when half of the atoms which are there uh, uh, in the ground state, they are in the excited state, then because the probability is same, okay, so what will happen, that the rate of stimulated emission will be equal to the rate of stimulated absorption. Rate of stimulated emission will be equal to the rate of stimulated absorption. So the assembly cannot have more than half its atom in the metastable state, never. So when the moment uh, when this is achieved, then there is no way that I am going to get the condition that n2 is greater than 1. Okay, there is no way the number of atoms in the metastable state is greater than the number of atoms in the ground state. So in this situation, laser amplification cannot occur, because for this we need a population inversion, and for population inversion, S2 has to be greater than N1. So the population inversion is only possible when the stimulated absorption are to a higher energy level than the metastable state alone, from which the stimulated emission takes place, which prevent the pumping from depopulating the metastable state. Okay, so in a three-level laser, more than half the atoms must be in the metastable state for the stimulated induced emission to predominate. So that is why, because we have two levels, now try to understand it again, because we have two levels, E1 and E2, this is metastable state. What will happen if the energy which I am supplying, so the probability of that through this energy, the probability of stimulated absorption through which the atoms will go from this state to this state is equal, that these energy are also responsible for these atoms which had gone from ground state to the excited state are coming to the ground state through stimulated emission. So when half of the atoms, the number of atoms are being same in these two states, the moment this will happen, the rate of spontaneous emission which are coming from this state to stimulated emission coming from this state to this stage will be equal to the stimulated absorption going from this state to this state. So there will be no way we are going to achieve the population inversion. That is, we are not, there is no way we are going to have the more number of atoms which are in E2 state than which are in E1 state. So we are not going to achieve the population inversion when we have only two levels, and when we don't have the population inversion, we are not going to have the lasing action. Okay, that is why we have at least three levels. Okay, you have seen that the more and more energy we apply to the system, more atoms are from the ground state goes to the excited state, and from there they come to the metastable state, and the moment we achieve the population inversion, number of atoms in more than in the ground state, we get a lasing action. Fine. Okay, for a four level lasing system, what we have a ground state, and we have some pumped states, the ordinary excited state, and then we have a metastable state, and then we have another intermediate ordinary state, and then we have a ground state. In three level system, we were not having this state in three level system. So why the four level system important? Because in the four level system, the transition from the metastable state E2 ends at an unstable intermediate state E1. Okay, this is between this state and this state. We are going to have between this state and this state, we are going to have the laser transition. So the population inversion is achieved between E2 and E1. Okay, rather than at the ground state E0. Because the intermediate state E1 decays rapidly to the ground state. Okay, intermediate state, the atoms which comes here very rapidly decays to the ground state, very rapidly, rapid transition. Very few atoms are in the intermediate state even. So because very rapidly they transit to the ground state, so very few atoms remains in the intermediate state even as compared to the metastable state even. So achieving the population inversion is more easy as compared to the three level system. Okay, hence even a modest amount of pumping the energy to the ground state is enough to achieve the population inversion greater than as compared to the three level system. That's why the four level lasing system is important over the three level system, because we don't have the intermediate state in the three level system, and the importance of the intermediate state is that the achieving the population inversion is more important. We have to supply the lesser energy in order to achieve the population inversion. That means the more atoms in the intermediate state as compared to the intermediate state in between which we have a transition. Okay, that is what the importance of the four level system. uh, I think this is all basic information you need to know about the lasing action and how the laser works. And in the next slides, we will try to understand some one or two lasers, how it works, like helium neon laser and ruby laser. Thank you.